This is the screencast for section 1.1, example 5. We're going to fit a curve to data. Previous, in example 4, we already kind of did this. We're going to look at a different kind of example. We're going back to the female prison population that we looked at in example 2, I believe. We showed in example 2, yep, there it is, that the percentage of females in the U.S. prison population had steadily been growing over the years. Model this growth graphically and use the graphical model to suggest an algebraic model. Now, I have already put in L1 the years and in L2 the female percentage of in prison populations. Instead of putting 1980 for 1980, I put the year 0, and then I made each year the annual equivalent after the year 1980. So 1985 when it is 5, 1990 when it is 10, etc. So please enter those into your calculators. Once you've done that, go ahead and go to stat plot, turn your plot 1 on, and zoom 9. Oops, I gotta clear out the equation from the last problem. Zoom 9 will show you a, pretty linear graph, actually. It's not quite linear, but pretty linear. So I'm going to say that this is going to take on a y equals mx plus b format. Now my y-intercept, year 0, was 3.8. So I know b equals 3.8. At 1980, 3.8% of the prison population was female. I got to find the slope, so I'm going to take two pretty easy numbers to work with. I'm going to use 0, 3.8, and then I'm also going to use 5, 4.4. So I'm going to do the change in y over the change in x, and I get that slope is about 0.145. So I think y equals 0.145x plus 3.8 is a linear model that would match that data. Again, the problem only says come up with an algebraic model, but I want to make sure that it lines up with my graphical model. So I'm going to put in y1 0.145x plus 3.8, and then I'm going to hit graph. And you can see that that linear model does a good job of representing the graphical model. Now for the now try problem, there's actually two now try problems, number 13 and number 15. Go ahead and put in your calculators in L3 the total in thousands, so it's 316,000 actually, people in prisons. Put in L4 the male population in the prisons. In L5 the female population that's different than the percentage. This is the actual population in prisons. Go ahead and pause this. I will wait. So number 13, now that you have the data entered in, number 13 wants you to model the data graphically with two scatter plots on the same graph. One showing the percentage of women employed as a function of time and the other showing the same for men. Measure the time in years since 1954. So we want the percentage of men and the percentage of women. Percentage of women is L2. The percentage of men, I'm going to have to calculate. That's going to be the number of men divided by total. So that's going to be L4 divided by L5, and I am going to put that into, let's say I don't have anything in L6 yet, so I'm going to put that in L6. Stat, edit. I'm going to go over to my list 6. And I'm going to tell list 6, hey, take L4 and divide it by L5. There's my percent of men. And we want to do this over time. So now I'm going to change stat plot 1. Let's see, that already has the percentage of women over time. Now I want to go to stat plot 2. I'm going to turn that on. I want to make that stat plot, though, the x values are still going to be the years. The y values this time are going to be the percentage of men, so I want L6. Second, L6. I'm going to clear out the equation I have in y1, and I'm going to zoom 9. So I'm going to zoom around all that data. There are my two stat plots showing the percentage of men and the percentage of women over time in prison populations since 1954. Number 15 wants me to model the data algebraically with linear equations of the form y equals mx plus b. Write one equation for the women's data and another equation for the men's data. Use 1954 and 1999 ordered pairs to compute the slopes. Well, luckily for us, we already did that in example 15 for the women. So I'm going to go, in example 5. Now we need to work on the men. I'm going to hit my trace key. Now 0, 3.8, I know that is a woman data. L1, L2 was the women data. Here's the men data. So my y-intercept for my men, if I hit up, I switch to the other set of data. My y-intercept, my b value for the men, y equals mx plus b. B is going to be 25.33. I have to calculate my slope, again, using two data points, so I can use this point that I'm on, 0, looks like 25 and a third. And then if I hit to the right, I'll go to the next data point, which is 5, 21.86. I get a slope of about negative 0.688, which makes sense to me. When I go back to the graph, the men's data was declining. That should have a negative slope. So I think y equals negative 0.688x plus 25.33 should be a linear representation of the graph I see using the men's data. I'm going to put the women data back in there. 0.145x plus 3.8. I'm going to put the men's data in there, negative 0.688x plus 25 technically it was 3 repeating. Let's see what happens. There's the women data that I already know lines up. There is the men algebraic line that also lines up pretty well.